marcher. Bien, bonjour, on va démarrer. Donc c'est la session Confiance, hein, ne vous trompez pas. C'est la bonne salle pour la confiance. Et si c'est pas la confiance, c'est pas la bonne salle. Et donc on démarre sans tarder, donc avec la présentation d'Émilie Kaufmann sur Privacy and Bandits. On va tous savoir ce que c'est que les bandits. Oui, en français, hein, il n'y a pas de... Enfin, c'est comme vous le souhaitez.
Sauf si quelqu'un veut que ce soit en anglais, levez la main et...
Et comme on voit rien...
Okay, so let's do it in English. So this presentation is to give an overview of the work we've been doing in the past year in the SCOOL team, mostly some colleagues of mine actually, on mixing differential privacy, a framework that some of you might know, with bandit theory. So in SCOOL we study sequential decision making, and so I will start by giving you or reminding you or giving you the definition of what is this bandit model that we study. So a multi-armed bandit model is a stochastic model which is given by a collection of probability distribution that we call arms. These arms are unknown to the agent who interact with them, and the interaction of the agent with the arm is sequential. So in each time step t, the agent selects an arm AT and thereafter collects an observation of the associated probability distribution that we sometimes historically called a reward. And the strategy is sequential in that the chosen arm at time t plus 1 can depend on what has been observed before. So the previously chosen arm A1 to AT, the previously observed reward R1 up to RT. And the algorithm is, of course, also allowed to use some randomization, which is independent on the past history, to take its decision. So, multi-armed bandit, there has been a surge of interest around these models in the early 2000s in the machine learning due to possible application to recommender system. So in this context, the arm would be, for example, different items like movies that you want to recommend to your customer. The action or arm chosen is which movie you put forward to user T. And then after you ask the user to provide some feedback on your recommendation, and this would play the role of the reward. So in that case, the rating could be some probability distribution supporting on 1 to 5 star, for example. But the example I like most to talk about is this old motivation in the statistics community in the 50s to model an adaptive clinical trial using a bandit model. So in that case, the arms are different medical treatments. The action is to give a treatment. Of course, the efficiency of this treatment are not known at the beginning for the current disease. You give a treatment to a patient, and then a few moments later, a few weeks, for example, you observe the efficacy of the treatment for the patient. So a simple model for the efficacy is just a binary random variable saying 1 if the patient was cured, 0 otherwise. And for the rest of the presentation, for simplicity, we will stick to this Bernoulli bandit model that are also very well studied for all these click or no-click models in recommendation. So this model is also good to exemplify the two kinds of bandit problems we've studied. So the first one is really connected to this notion of reward, and that you try to maximize the cumulative reward, as in a reinforcement learning problem. Because of the randomness, typically you look at the expected sum of reward, even if we could look at some other characteristic of the reward distribution. So this is a well-studied problem. And another possible objective for the pharmaceutical company is not to cure patients during the trial, but after, and so to be confident in knowing which of these arms was better. So I will denote by mu the expected reward, in the case of the treatment, the probability of efficacy of the treatment, and the goal is to discover the arm that has the best mean. So these two problems have received an extensive treatment in the bandit literature. So the regret minimization problem, the one where you try to maximize the expected sum of reward, has been studied, I would say, first. And so maximizing the expected sum of reward is equivalent to minimizing the number of selection. So NAT is the number of time I selected arm A up to time T. And so for all arms that are not the best arm, you want to maintain a low number of selection. And actually, we know very well how low it should be on a simple model like the Bernoulli Bandits. So we have a lower bound saying that for large T, the expected number of suboptimal selection cannot be arbitrarily small. It has to be of order log T. And we even know that here there is a constant which depends on the KL divergence between the distribution of arm A, Bernoulli, and the distribution of the best arm. And there exists algorithm matching this lower bound. For best arm identification, now the status is a bit the same. So best arm identification is about finding A star. So we are not evaluated by the chosen arm and how many times we selected the bad ones, because we are allowed to do it. The goal is to make actually a guess of the best arm, and we will be evaluated by the accuracy of this guess. We want that we want to have a small probability delta to make a wrong guess at the end of the experiment. And furthermore, we can decide to stop the collection of data at an adaptive time. So for best arm identification, an algorithm is made of these three components: selection rules, that is adaptive; stopping rule, when do I know which arm is the best, and then the guess you make. And so there the metric is the sample complexity, the total number of samples we took from all arms. And the sample complexity is also known to be lower bounded by something which depends on the error we allow ourselves to make. And here also some information, theoretic quantity. I will give a hint about it later. And there also exists algorithm matching this lower bound, at least in a regime where you get your error to be arbitrarily small. So the problem is kind of solved. But what if now, still in this simple Bernoulli model, we assume that the observations can be sensitive? In particular, in the clinical trial example, at the end of a trial, you have to publish which treatment have been given to it in which order. However, you might don't want to disclose some private information for the patient who was cured or not. Like if an evil insurance company look at the output of the clinical trial and manage to infer whether or not their client is in good health, this is bad. So this is the research done at SCOOL has been on this trying to characterize the trade-off between optimality, that I showed you on the previous slide, and how we take this privacy constraint into account. And so I will be mostly talking about the work of Debabrota Basu, a colleague of mine, done mostly with Ashraf Aziz, who was a PhD student who started before Foundry, and now we are keeping on some research direction. So privacy is usually something which is defined in a batch setting. So it is the privacy of any mechanisms that takes and inputs some usually fixed size data set and then gives some output, and the mechanism is better be randomized because differential privacy states that basically the probability of any output has to be close under, sorry, here there is a missing, oh, we don't see the primes. But basically, if we take two neighboring data sets, so two data sets in which only one row has changed, so only one individual has different values, then basically the distribution of the output should be close, and the closeness is measured with this privacy budget. So the first question, so there has been many papers on privacy and bandits, but it's not so easy to give a good definition of privacy in the bandit context, because usually the data is collected on the fly. But the one I like the most is the one on the left. How do you turn a bandit algorithm to a mechanism? Well, it takes as input all the possible reward you could have gotten. Like here you have your patient here, and here you have the treatment. And you imagine that you could have given all the treatment to each patient. Of course, in the bandit algorithm, for each patient, you will only observe a single treatment, but virtually this table of reward exists. And then the bandit algorithm becomes a mechanism that takes as input a table of reward and then output a sequence of successive actions that were chosen by the algorithm. And so this is called the table DP view. Otherwise, you can also have it as a mapping from the reward to the action. But what is important is that here the constraints are only on the coin flip of the bandit algorithm, not on the reward. And so for best arm identification, it is even a bit more challenging to properly define DP because the algorithm was made on this adaptive, we don't even know the size of the dataset before, and so to define privacy properly in the context of best arm identification, we have to, we define it by saying that for all possible lengths of dataset T, and for all possible table of reward of size T that differ by at most one row, where the data for a given patient could be made different, then you want that the probability to have observed a particular reward sequence, to have stopped at time T, and to have recommended a certain arm A has to be close under the two neighboring table of rewards. So now I will try to give you some ideas on how we basically what needs to be modified on existing results for classical model due to the privacy constraint. And our focus in the literature, at least in the problem-dependent literature, has really been to look at lower bounds, because then they give us first a criterion, and then they can even inspire some algorithm. So how are the bandit lower bound modified by privacy? So first I have to explain you briefly how we derive lower bounds in bandits. So lower bound on what? In the regret world, what I showed you a lower bound was on the number of times we select a particular suboptimal arm. In best arm identification, it is a lower bound on the sum of all these selections. And this lower bound comes from change of measure arguments. And in particular, if you want to give a lower bound in some bandit model whose means are mu1 up to mu k, we will consider an alternative model lambda, in which another bandit world, which differs, in which the identity of the best arm differs, because you expect your algorithm to have a different behavior under these two models, and because you expect the behavior to be different and that still the algorithm is going to be correct on both problems, you can actually give a lower bound on the distance on the two models. So those results, which are a bit in the same flavor in regret and best arm identification, are obtained by some information theoretic arguments, and they can be phrased as lower bound on the KL divergence between the observation, the distribution of the observation under the model mu that you care about, and the distribution of the same observation under an alternative model lambda. And so if this KL large will translate into the number of selection being large. This is because this KL in a bandit model can be actually connected to the expected number of suboptimal selection, and here to the KL divergence between the distribution of mean mu A and the distribution of mean lambda A. So this is the usual, usually we stop here and then we try to find good lambda. But what if there is privacy? Actually, privacy is expressed some constraint usually on neighboring datasets. If you have two very close table of reward, you know that the probability of any events is going to be to satisfy this inequality. This is just the definition of epsilon dp. In a bandit mechanism, your rewards are drawn at random. So the first step is to look at what happened when, additionally to the randomness of the algorithm, you take into account the fact that D and D prime can be drawn IID from two distributions P and Q. And in that case, there is a nice result by Karwov Adam in 2017 that says that you can also relate the probability when you add some data generation process, and this is connected through the total variation of the generating probability distribution and the number of samples in the batch dataset. And so what my colleague did is that they provided a sequential version of these results that would fit the Bandits model, and that somehow is extending this. And it is in particular relating the KL divergence between the distribution of the observation of the two models to here a sum of expected number of selections multiplied this time by the total variation distance between the distribution with mean mu A and the distribution with mean lambda A. And so what this gives us is, instead of the constraint we usually have to prove lower bound in Bandits, we get an extra constraint where instead of having a weighted sum of number of pool times KL, we get also a weighted sum. Here it's in the Bernoulli case, so the total variation is just the L1 norm between mu and lambda. And so we get this extra constraint. And so what we do from here in best term identification is to try to get the best lambda in order to get the tightest possible bound on the quantity we care about, which is the sum of these without the KLs. So you could write this as a minimum of these sums constraint to the linear constraint, but usually we will write things as a problem, a saddle point problem, a supremum over all possible allocation over arms. So this is the simplex of size k. And here an infimum over possible alternative lambda where the best arm is different. And so in usual best arm identification, we don't have this minimum of two terms. We just have the first one. So this is the T star of mu I showed you in the previous slide. So the expression is a bit ugly, but then you can still find ways to compute it. There is a lot of paper who do that, but this is not our focus here. I just want to show you how the results are transformed with privacy. And you can also do the same and ignore this term to get an upper bound, and you would get a bit the same quantity, except that, again, the KL divergence is replaced with a total variation distance. So you can prove that this complex lower bound that we can prove is always lower bounded by the maximum between T star of mu, which is the lower bound we know how to match when there is no privacy guarantee, and the privacy gives us the maximum with this other term that, thanks to the Bernoulli distribution, has a closed form and is just a sum over inverse gap. And so this suggests that when epsilon is large, the maximum is going to be unaffected. It's going to still be T star of mu, and privacy can be achieved for free. But when the maximum is equal to this term, so when epsilon is small, then privacy is the dominating part of your sample complexity. So this is currently how we proved bound for privacy. Well, my colleague did. And so now, how do we design algorithm? Just quickly. So what my colleague proposed was a lot of, so I will not present you in details bandit algorithm, but those algorithms, as you may expect in a simple Bernoulli world, will rely on estimation, of course, of the unknown mean of each arm. So usually the estimation is you take all the observation you got from an arm and you average them. But here, to get privacy, it's a bit dangerous to do that. And to prove privacy, actually, my colleague proposed this doubling and forgetting estimator, where the idea is not to keep all the observation, but basically to update this estimator only once in a while when the number of selection of this particular arm has doubled. And then, to do the estimation, you use just the data from the previous phase. You get rid of everything. And after that, you add some noise to the estimator, some Laplace noise. Because for the non-sequential setting, having privacy mechanism for estimating an empirical mean is well known, is by adding a Laplace noise with the appropriate parameter depending on the sensitivity, which is 1 over the number of samples. And so with this trick, if you want to make a privacy analysis, you can always, if you look at a particular line in the table of reward, you can always say that this line contributes only to an episode. And because the algorithm takes decision based on these mu tildes, which are private, then you can prove that the mechanism is epsilon dp. So basically, you take any existing algorithm, you just replace your estimator by this doubling and forgetting ones. And of course, you still have to change something. So typically, in best arm identification, an important component is the stopping rule. And the stopping rule is comparing. You stop when you see a significant difference between one arm and the other in terms of empirical mean. So this time you are no longer using the empirical mean, but this noisy and subsampling estimators. And so what my colleague proposed is a way to recalibrate the threshold traditionally used in best arm identification algorithm and to get something private. And then they did an analysis for different possible BAI algorithms. So for example, this adapt for the wrapper mechanism that I presented, TT for top 2, which is some family of algorithm. They managed to prove a bound on the expected sample complexity divided by log 1 over delta. And this bound scales like T star of mu, so the complexity without privacy, multiplied by something that depends on epsilon. And when epsilon is small, basically the dominating term is this T star times the maximum gap over epsilon. And for instances in which all the gaps have the same order of magnitude, we can argue that this is off order the lower bound. So it's a bit rough, and in particular, this factor 4 is due to the doubling mechanism and seems quite hard to avoid. So compared to what we have in traditional algorithm, we don't have lower bound and upper bound that are exactly matching. So before showing you some perspective, here is just an illustration of, so TT-UCB is the vanilla best arm identification algorithm. So this is an estimation of its expected sample complexity for different value of epsilon. So this algorithm is not private, so this is a baseline that doesn't take privacy into account. And then we have different algorithms that were proposed, and this was the previous algorithm relying on elimination. And what I just wanted to show you is that we see this, for some time there is no, the sample complexity does not seem to depend on epsilon. And then there is a kink where here we enter the high privacy regime, where indeed we see this 1 over epsilon regime that appears. Okay, to conclude, what we try to investigate now within Foundry is try to get really matching upper and lower bound with constant 1 with privacy. And so Deba Brota, Ashraf, and other colleagues from Japan recently make a nice progress on this problem. So this is something they recently submitted to COUT. So they managed to prove tighter lower bound, where instead of having a maximum of 2 terms, they defined a new information theoretic quantity, which is kind of an interpolation between the TV and the KL. And they also managed, in the Bernoulli case, to have new concentration results that directly take into account the fact that we sum Bernoullis with this Laplace distribution in which we add noise. And with that, they have no matching upper and lower bound for the regrets. And so what we are working on with a PhD student who started recently within Foundry is to work on the best arm identification counterpart of this problem. And right now we even look at simpler, just sequential testing problem, where the question is just when to stop and that we don't control the data collection process. So that's it. Thank you for your attention.
Thank you, Émilie. So we have time for questions. Yes.
Les questions?
Merci Émilie pour le super exposé, c'était très clair. Est-ce qu'il fallait parler en anglais?
Comme tu veux, je peux répondre en français.
Juste avant, donc, si dans le graphe sur les résultats, voilà, ouais, tu dis la baseline en bas, elle n'est pas private.
Oui, c'est un algorithme de BAI qui
Oui.
s'appelle TTUCB, à quel on n'a pas donné epsilon, donc c'est juste la sample complexity si on n'essaye pas d'être DP.
Voilà, on n'essaye pas d'être DP, mais par exemple, dans du Thomson sampling, on fait quand même des tirages qui sont un peu aléatoires. Et alors, ta borne 9 semble dire que la contrainte de confidentialité différentielle, elle n'est pas active quand le niveau de confidentialité requis est relativement grand. Du coup, on peut se demander si dans ces régimes-là, un algo classique, comme du Thomson sampling ou quelque chose comme ça, ne serait pas automatiquement DP. Et finalement, est-ce que tu as des garanties qu'il n'est pas DP?
Il y a des articles justement qui donnent le niveau de privacy. Effectivement, TTUCB, là, c'est pas un algorithme randomisé, donc il n'a pas aucune chance d'être DP. En revanche, il existe des algorithmes randomisés, dont Thomson Sampling, dont parle Aurélien, et d'autres adaptations au cadre BAI. Et en tout cas, il y a des articles qui essayent de donner le niveau de privacy de Thomson Sampling en disant qu'il en a une certaine for free. Mais si on veut un epsilon donné, il va quand même falloir, par exemple, gonfler la variance du Thomson Sampling pour être sûr d'arriver à un epsilon. Et je ne suis même pas sûre qu'avec Thomson Sampling, on puisse effectivement arriver à n'importe quel epsilon. Parce qu'habituellement, on rajoute plutôt des bruits de Laplace. Thomson Sampling, dans ce cas-là, le bruit, ce serait une certaine distribution bêta. Donc, il faut faire des calculs non standards pour bien montrer qu'on matche un epsilon. Et je ne suis pas sûre qu'il existe des variantes qui te garantissent exactement le epsilon.
Thanks from my end as well. I'll do mine in English. Sorry.
No problem.
And it's actually related to your last point. It's a technical question because I'm not very familiar with this type of algorithms, but why, what is the operational benefit of Laplace noise precisely? I mean, what does it give us technically?
It's just that the Laplace mechanism is a well-known mechanism in the batch privacy community, so you know how to calibrate the noise if the mechanism has a certain sensitivity. So the sensitivity is the maximal change you could get if you just change one observation by the largest possible range. So when you look at an empirical mean, the sensitivity, if you average n items and can change only one, it will change by up to 1/n. And so it is a Laplace mechanism. If you add the noise to be sensitivity over epsilon, you know that this is differential private. If it's a batch mechanism with n data points. And so what we try to do is just to resort, just to have not a lot of different, like usually in Bandits the estimate change at every time, but this is hard to manage because privacy will just increase if you add noise in every time. So the idea to not pay too much by adding noise all the time, which hurts a lot the utility, is to do it in batches and once in a while add noise. So this is the idea of the doubling and forgetting estimator. The phases are of exponential size, and in each phase you reset the estimator only when the number of selection has doubled. And in each, then the estimator is frozen to using the data in the previous phase, and there you have applied only once a Laplace noise to this estimator. But you could add other type of noise like Gaussian and then get other type of DP, because here I stick on the vanilla epsilon DP distribution, but you have another framework called Rainy DP, or sometimes you add also a slack plus delta. There you can also, you have this similar mechanism with Gaussian noise. But Laplace is a typical noise we add when we really want this epsilon DP constraint I showed you.
Okay, the last part was perfectly helpful. Yeah, thank you. Thank you.
le micro.
Merci.
Et je m'occuperai des questions-réponses à la fin à chaque fois.
D'accord, ok.
Ça, c'est parfait.
Okay, so net presentations will be made by Goubault with a very simple title. A Zonotopic Dempster-Shafer approach to the quantitative verification of neural networks.
Thank you, François. So this talk is going to be about formal verification, right? Let me see which sense. Okay, which direction? Okay, so it's going to be about verification of neural networks, verification in the sense of formal methods. So I won't go into lengthy discussions about why formal methods in AI. Just think about, an autonomous car, the control of which is implemented using a neural network, and the perception of which is also implemented using a neural network. So I guess you'd agree with me that you would need some formal guarantees that the car would behave correctly, right? The question is about, the question really is about what sort of properties and what sort of hypotheses you may want to get. So in this talk, I'm going to restrict to the basic block of properties we can think about. So that's going to be input-output relations. So given some sets, here it's a product of intervals, some sets of inputs given to the input neurons here, determine at least some outer approximation of the set of values that the output neurons can take, and check whether these output neurons comply with some simple specification, let's say some linear inequalities, for instance. So here you see that we can say it's not in the error zone, so it's going to give you true. If it were entirely into the error zone, you'd have false, and if it's sort of mixed in between, you'd have no proof at all of whatever, right? Okay, so that's the sort of classical ways neural networks are being verified in 95% of the literature, I guess. So that's called qualitative verification. But indeed, it may be interesting to get one step further. So it might be interesting to go to what we call quantitative verification. Quantitative verification is about qualifying, the level of truthfulness that some property has for some neural network. And here it's going to be the probability, or at least probabilistic bounds on the truthfulness of some property. And so certainly we need some probabilities to begin with, right? So just think about perception, as I was mentioning before. You're going to suppose that the sensors you have some noise, maybe some Gaussian noise of some more or less known variance, of some more or less known means. And you're going to try to propagate these distributions throughout the network to get some distributions on the output, and then decide of the truthfulness, the probabilities of the truthfulness of some property. So indeed, what we're going to manipulate as well is sets of probability distributions, because in general, you don't really know for sure what the variance of the noise may be, or you might know it, but you don't really know on which sort of real sets of values you're going to apply this. So you're going to have unknown mean, for instance, but known variance. And so that defines sets of probability distributions. Let me sort of conclude here, if you fall asleep, just to say what we're going to obtain. So we're going to obtain a guaranteed analysis, so guaranteed probabilistic bounds on the truthfulness of some property, given arbitrary sets of distributions as inputs, and not as in competing frameworks as a prob star here, restricted to Gaussian distributions. And we're going to be, in general, at least as precise as the competition, right? So prob star, and in always actually faster than that. So after this self-satisfying presentation, I'm going to dive into details. At least I'm going to tell you how the problem is formalized and on which sort of basic blocks, this analysis is going to be constructed. So formally, we're doing as in PropStar. We're going to define the inputs as sets of probability distributions whose cumulative distribution functions are going to be bounded by this lower sort of probability, CDF function f underline, and the upper CDF f of a line. And we're going also to specify the support of the function as some kind of polyhedra. So that's linear inequalities here. And from this specification of inputs, we're going to try to find guaranteed bounds that the safety property, so H is a matrix, Y is the set of the vector of output nodes here. So H of Y is less or equal than some vector of values. So that's the linear guards I was mentioning before as well. So in this talk, we're going to restrict to feed-forward ReLU networks. So we could actually consider other activation functions. The ReLU function is the simplest one for this presentation. We're not going to deal with recurrent networks, for instance, which means much more involved analysis methods, far beyond the presentation today. And just to give you some explanations of the things I'm going to introduce, I'll be using this simple example. So this neural network, which is huge, right? So which has one hidden layer, one linear output layer. So the weights are indicated on the edges here. The biases are all zeros. And just to make sure we're on the same page, I remind you the qualitative question we're going to ask on this thing. So given these inputs, the two input neurons being between -2 and 2 and -1 and 1, does the output satisfy? The first output is less or equal than -2. The second output is greater or equal than 2. That's the qualitative verification problem. The quantitative one, which is the one I'm dealing with in this presentation, is about the same. It's just we're looking at the probability that these properties hold true. Given some input hypothesis, let's say it's a uniform, the first neuron is sampled from a uniform distribution between -2 and 2, as with the second input, or a normal distribution, for instance, with unknown variance or unknown mean, okay? So if there's not any questions at that point, I'm going to tell you about the basic blocks of this analysis we're carrying on. So it all relies on the notion of imprecise probabilities, which exists since the 60s, I think, last century. So I'm going to take some time to introduce these P boxes and Dempster-Shafer interval structures, which are really at the basis of the whole thing. I'm going to present a fairly naive analysis using directly these concepts for neural networks, and then see what the problem is and try to find ways, and that's going to be our analysis, of course. So there are actually two ways to improve and have a non-naive implementation out of imprecise probabilities, is these probabilistic sonotopes or these DSZ structures I'm going to introduce. Okay, so what's a P-box? What are these imprecise probabilities? That are sort of tools to represent sets of probability distributions. And P-boxes are the easiest to understand. They're just defined as a pair of functions. So f of the line is called the belief function. F of a line is called the plausibility function. And they're going to be the lower and upper bound of the CDFs of all probabilities you're going to consider, right? So P-box contains all the probability distributions that have CDFs comprised between the belief and the plausibility functions. So of course, if plausibility is equal to belief, you get exact CDFs, so that's an exact Gaussian CDF. If on the contrary, you get, for instance, plausibility being 0 on all support, and no, that was belief, sorry, and plausibility being 1 on all the support, then you're going to get all probability distributions on that support, right? So it's like a non-deterministic kind of value. You have no distribution whatsoever, or no knowledge of any distribution whatsoever. And this is, as you can see, two CDFs of Gaussians. And this abstracts, for instance, the set of Gaussians that have mean value between 0 and 1, but variance which is known to be 1. But indeed, within these two bounds, you don't have only Gaussian CDFs, you may have many other distributions enclosed in that. So in that way, it's an abstraction. It contains much more. It's much less precise than what I intended to represent at first. Okay, so there's actually a more algorithmic way of looking at p-boxes or particular p-boxes, which is these Dempster-Shafer interval structures. The point of view is slightly different, but they're going to represent somehow all p-boxes with staircase, plausibility and belief functions. And the way it goes is you're going to choose a set of what's called focal elements, so a set of subsets of the set of things you want to measure, right? So here we want to measure things in real numbers, so we're choosing focal elements to be intervals. And to each of the focal elements, you're going to associate a weight. The sum of the weights is going to be equal to 1. And you have two canonical ways, let's say, to interpret this structure. You can interpret the probability, you can interpret optimistically or pessimistically the sort of CDF functions that would agree with that structure in the following sense. That is, if S is some set of real numbers, you could say that given that DSI, the probability of S is less than the sum of the weights of all focal elements which intersect S. So each time you intersect one of the focal elements, you count the weight as if you had the entire focal element, right? It's optimistic. And the other way, which is pessimistic, is to say, okay, I'm only going to count the weights to give you some idea about the probability of the set S, or the measure of set S, when just the weights of the focal elements that are fully included in S. Okay? So here, for instance, you have for values between -0.5 and 0.25, they are in two focal elements, so it's here and there. So the optimistic thing is to count both weights, so it's going to be bounded by 0.3, and the pessimistic thing is to say that it's included into the first one, right? So that's going to be greater than 0.1. Okay, so in some ways it's not bijectively, DSI are not in bijection with p-boxes and not even with staircase p-boxes really, but they're sort of linked intimately in some ways. So from any p-boxes you can take upper approximation, lower approximation in terms of staircase functions. And from these staircase functions you can deduce some focal elements which will produce these p-boxes as I was mentioning before, using these pessimistic and optimistic interpretations, right? And you just have to decide the number of focal elements, their sizes, for instance. So that's different approximations by the size of some p-boxes here. And with more focal elements, you get something closer, of course, as with any staircase functions. Okay, so using DSIs, you get all the classical set-based methods, at least in intervals, because we're dealing with intervals right now. So you get all the interval arithmetic at hand. And so, in fact, you can derive arithmetic operations on DSIs in general, based on interval arithmetic. So you can derive interpretations of addition or any linear or affine function on a given DSI. What it will give you is basically what it will be based on. Basically, is applying these linear functions on all focal elements somehow, all pairs of focal elements in the case of the addition. And you have some computation of the resulting weights associated to each of these sums. But these weights will depend on different hypotheses. So you have two sort of extreme hypotheses you can make. In general, you may have all sorts of in-between copulas you may want to look at. The two extreme cases are when you sum two DSIs which are independent in the sense of probability theory. Then you would get this, for instance, for these two sort of uniform values for x and y. So something pretty thin, pretty precise. But then the extreme other case is unknown dependencies. You have no idea about dependencies. Y may be minus X, or Y may be completely independent of X, you don't know. And then, of course, what you're going to produce, the computation weight, will give you something much larger. You get to be much more imprecise in the description of the set of resulting distributions, of course. Okay? So these are well-known things. So what was not well-known, but it's pretty simple to derive, so it's the interpretation of the ReLU function or some other nonlinear activation function. So the ReLU function, you just need to apply it to each bound of the focal elements, and the resulting DSI will give you what you expect. That's the ReLU of that set of probability distributions. That's pretty simple to compute algorithmically. So given these interpretations of affine functions and ReLU functions, you can derive a very naive verification technique for input-output relationships in neural networks, in ReLU neural networks. It's just going to be, you're just going to traverse the set of layers of the neural network and interpret for each layer the affine transform on the resulting DSI from the previous layer, then apply the ReLU function we've just seen, and iterate, and then interpret the guard and get the probability distribution, the probability bounds, the lower and upper probability bounds from the lower and upper P-box CDFs, so from the belief and plausibility functions. So what it gives you is sort of good enough sometimes, but sort of disappointing as well, as you will see. So that's my simple example. You have uniform distribution, which is discretized by 10 focal elements. And you get with, that's, I don't recall this one, probably a non-dependency, I think. So you get this output and this output for the second neuron, which is not very thin. And even though you're going to add more focal elements, there are hundreds of focal elements for the inputs now, you just get something which is not much different, right? I mean, it's just a bit more precise on the edges, but it's going to have the same range overall, okay? Okay, so if we change things, if we look at Gaussian distributions, you'll get something fairly similar as well. That's an example where we discuss the unknown dependency, which is on the left, with respect to independent inputs on the right. So, of course, independent inputs gives you much more precise probability bounds. So you see these probability bounds are the probability bounds I wanted to get on output neurons, that one less or equal than -2 and then 2 greater or equal than 2, are going to be pretty wide with the unknown dependency hypothesis, whereas they are much I mean, more precise when you have this independent inputs hypothesis, okay? Okay. So what happens really is that, of course, you are basing the whole hypothesis on interval arithmetic, and it's well known that interval arithmetic is not very precise when it comes to even linear transforms. So what we did was to change the underlying interval arithmetic to use one of our favorite arithmetic, which is the affine arithmetic, which is some sort of sub-polyhedric abstraction of sets of states. It's called Zonotops, and Zonotops are actually just central center-symmetric polytops, compact polyhedra, with center-symmetric faces, which have a nice parameterization. They're just affine transform, so C is a vector and gamma is a matrix. It's an affine transform of a unit hypercube, so it's just parameterized as some linear transform on these epsilon variables, which we call noise variables, which take values between -1 and 1. And here's an example of such a zonotop, just a parallelogram in that case. And of course, all linear transforms or all affine transforms are exact on zonotops, contrarily to intervals. Okay, so it's going to be fairly precise on the linear layers. The only problem is, of course, the nonlinear transforms, like the ReLU transformer. You need to get some center-symmetric polyhedric approximation of the graph of the ReLU function, which is in green, between LX and UX. And the one which minimizes the surface is going to be given by some formula I'm just hiding, but it's going to be that sort of thing as a picture. Okay, and then knowing that we can replace, trying to replace interval arithmetic by with Zonotops, there are two ways that we considered doing so. The first one, I'm not going to show you in great details, is what we call probabilistic Zonotops. So the idea is to associate a Zonotop which will give a value, which will relate the values of all nodes within a neural network, given some noise symbols, some parameterization of the inputs using noise symbols. The only thing we are changing with respect to classical Zonotopic abstraction is that these noise symbols, they're not just non-deterministic values between -1 and 1. They are given some sets of probability distributions attached to them, and that these are given using some DSI, some Dempster-Shafer structure on intervals. And so basically we're combining Zonotops with DSIs, and we sort of propagate these two computations along the different layers of the neural network. So probably the more interesting way to use Zonotops, which gives the best results, are these DSZ. So there, the point of view is slightly different. You're going to use Dempster-Shafer structures, but multidimensional ones, where the focal elements are going to be Zonotops. So you're going to attach weights to Zonotops in Rn. So n is the number of nodes in your neural network, at least nodes in some layers. And we are going to give arithmetic interpretation of the different layers in terms of DSZ, or at least going to be for you in the paper, which has been published in Formal Methods 2024 and end of 2024, if you want to see all the details. So just to tell you how to interpret these things, so I told you these DSZ, it's just Dempster-Shafer structures using Zonotops, these center-symmetric polytopes, as focal elements. You attach weights to them. So they describe basically sets of multidimensional probability distributions that have CDFs given enclosed within two bounds. And that's the same trick as before. These two bounds are given by sums of the weights of the Zonotops which intersect this set you want to measure, right? The set of values below some value V. And the lower bound is going to be the sum of the weights of the attached to Zonotops which are fully included in the set below V, okay? Just a basic extension of DSI. So you're not going to read that algorithm, but what we're going to do is indeed propagate these Zonotopic focal elements through the different layers, the linear layer and the ReLU function we are approximating as I showed you in one picture. And at least in that particular case, if we suppose that the input neurons are independent, the calculation could be made very simple in that you just propagate the focal elements and then the weights that are attached to each propagated Zonotops, focal element, is going to stay the same. If you were to use different copulars, then that would be much more complicated, but I'm not going to give you any details today on that, okay? And then you can measure on this multidimensional Dempster-Shafer structure the lower bounds and upper bounds of the specification you want to test. Okay, so let me just finish in 5 minutes, 2 minutes, okay, 3 minutes. Okay, so you can play with the prototypes. It's written in Julia. It's based on many nice packages such as probability bounds analysis, for instance. And you can see at least, so I won't look at the toy example. Let me just show you two classical examples from the literature. So the ACAS-XU, an anti-collision system made of 45 DNNs of I think that were like, yes, 6 hidden layers, 5 inputs, 5 outputs, and they're supposed to tell a pilot of some planes whether they might run into potential collision with another plane, given the 5 inputs giving you the relative configuration of the 2 planes. And it will advise the pilot whether to turn right, strong right, weak right, or left, or weak left, or clear out of conflict. So that's the 5 output neurons. And you want, of course, to prove that under some circumstances you have clear of conflict, or you turn right and not left, and that sort of things, okay? And you see that, so with respect to the competition, let's say, to PropStar, we get very often fairly small bounds, or at least comparable or even smaller bounds. Guaranteed bounds, because these properties are exact. You should find probability 1, whereas PropStar doesn't find that it can be probability 1. And all this in a time which is much less than the time it takes for PropStar, which is even parallelized on 8 cores, and our implementation is not yet parallelized, I must say. Okay. Okay, so the other example, which is well known, is the rocket lander, so some kind of SpaceX landing thing, and you want to check that it's not going to tilt the other way when landing. And there again, there's, let's say, 100 nodes neural network controlling this stuff, and you see there again that the precision is much better, and with a time for computation which is much smaller, okay? Okay, so I'm going to stop here. So there are tons of things to do from there. There's some restrictions about unbounded support and about independence hypotheses were made, which can be relaxed. That's still future work, partially at least. The representation is quite still costly in many ways, so we were thinking of improving that and not having this staircase phenomenon, which is kind of complex to deal with. And also we want to check much more complicated specifications like quantified, like specifications using quantified logics. Okay? Thanks a lot. Thank you.